Hi guys, I'm going to do a second video here on the material very much related to 8.2, but it is not part of the textbook. And now you say, oh professor, why are you doing this to us? We have already so much to learn, this is too much. I'm doing this because I think it will help you better understand what goes on. And I also will assign some separate homework problems for that you can practice this a little bit. It's basically turning things a bit around. And so if you look at the title here, finding linear homogeneous recurrence relations with constant coefficients. So the rest of the title is all about this thing that we've been studying in the other lecture. But now we're not trying to solve them, we're trying to find them. Now, before I go there, let me just again quickly remind you how did we solve. So if you have a recurrence relation, what did you do? The first step was you found the characteristic equation. Okay, and this characteristic equation is something you could basically read off or construct from the original recurrence relation. Okay, keep that in mind. So what you then did was you solved this one, but you needed to do a little bit more. You needed to find the roots with their multiplicity. Right? This is in when we did quadratic, that was a simple case, but now we want also the roots with the multiplicity. So suppose you have a root A. So A is a root. Let's make it singular here, one root, but there are of course many roots. And suppose the multiplicity is with multiplicity E, D, let's call it D. Okay, there are more. So what happens then when you have a root like that? We know then that the contribution to a general solution remember that was step 3, right? In step 3 we said, okay, this is going to be the general solution, and we have alpha, betas, and gammas, and so on. And what we're trying to say there is that if you find the right alpha, beta, gammas, and those depended on the initial conditions, then you have the solution that you want. And basically meaning that any solution was built up from these solutions that you derived from just knowing that A was a root and that the multiplicity was D. So how was this how did we do this? Well, we said if A is a root, then you have A to the power n. So you get this geometric series, that will be part. Oh, okay, perhaps I shouldn't take A here. Let me take a different letter. Let me call, what do you want to call the root? Let's call it B. No, C. Let's call the root C. I'm saying that because we write AN, right? So I don't want to confuse the A's with that. So the root is C, and the multiplicity, let's call the multiplicity M, sorry. I just want to get a little bit. So what do we say? Okay, AN, that is a whole bunch of things, but the contribution of this particular root, well, that was this root to the power n. N was the index, right? And then what did we have here? This was a polynomial. Here we put a polynomial of degree. What was the degree of this polynomial? 1 less than the multiplicity of degree m minus 1. And that was a general polynomial, meaning the coefficients of this polynomial were these Greek letters, alpha, beta, gamma, and so on, that we did not know yet. Okay? That's how we built this. And then we would determine this alpha, beta, gamma, and so on. Now, I want to turn things a little bit around. And I'm going to say this. Suppose now that let AN be given by the following formula. Okay? 3 plus 2n to the power n plus 1 minus 5n minus 1 to the power n. So this is now, I'm giving you a series, a sequence, sorry, I'm saying series, sorry, I meant to say sequence. I'm giving you a sequence, and this is going to be a geometric, this is no longer a geometric sequence, right? But you see the 2 to the power n is there. And it looks like the original form. It looks like a special form here, right? There is this exponential part, that is this one here and this one here. And then there is this polynomial part, that is these guys and these guys. So let's now think backwards. How did we get from this root and this multiplicity, we got to here, right? So let's now think backwards here. Can I determine from this what would be the root and what would be the multiplicity? I'll let you think about it. So pause the video if you don't see it right away, but I'm going to continue. The root is clear indeed. So the root will be 2. And what is the multiplicity? Remember, this was 1 less than the multiplicity. So the multiplicity here will be 2. I mean, the degree was 1 less. So the m will be 2 here, and the root will be 2. So in the characteristic equation, we would have this particular guy would come as r minus 2, the root, to the power 2. Sorry, both numbers are 2, but this is the root here, right? The root goes here, and the exponent goes there. And then the same here. What is the root? Here the root is minus 1. And what is the degree here? The degree is 1, so the multiplicity m is 2 again. So here we would have x minus minus 1 to the power, this power 2. So this is the characteristic, r here. We used r as the variable in our characteristic equation, so let me stick to that. So this is the characteristic equation that would tell me the general solution would be given in this way. Okay, so here you would have not a special polynomial like 3 plus 2n, but you had the alpha plus beta n. And here we would have gamma plus delta n. But we know what alpha, beta, gamma are because we have given an, so we know that these are the solutions already. So we don't have to worry about finding them, we have them already. By the way, what we're trying to do is not go this way, which was in the first video, we're trying to go that way, in the opposite order. So we have the characteristic equation, and now I said, remember, the characteristic equation, it was something that you could easily find from the original recurrence relation. How did that work? Well, first of all, unfortunately, we have to expand this now. It's a little bit annoying. So r minus 2 squared, that is a double product formula, r minus r squared minus 4r plus 4. And this one, the double product formula is r squared plus 2r plus 1. I hope you agree with that. But now you have to multiply it out. That's a little bit of an annoying thing. I like to multiply things out like this, like a little bit when you do regular multiplication. I put them underneath of each other. And then you just multiply. I'm going to use 1 and I multiply this here. This is 4 minus 4r, r squared. Okay, so that multiplying 1 with all the 3 guys on top. Then I do 2r, multiplying with these 3 guys. 2r times 4 is 8r, but where am I going to write this? Of course, I'm going to write it here, right? That's the same thing is what you would do if you would multiply, if you would say, for instance, 143 times 25. What do you do? Well, you do 5 times all these numbers. That carry over, that's no carryover here, so that makes it even easier. 20, so 21, and then 5 plus 7. But then when you multiply with 2, that's because they are now tens, decimals, the digits of 10. We write 2 times 3, 6, we shift it that way, right? And we do the same thing here. So 2 times r, that's 4. Now 2r times minus 4r, that is minus 8r squared. And then that is 2r cubed. But we still have to do this one. So that would be a 4r squared, which I now put here, right? And so what I'm doing now is taking r squared and multiply each of these 3 terms with r squared. And so that would be a minus 4r cubed. And then finally r to the 4th. And then you add them like we would do here too, right? So okay, keeping on my analogy here, well, it's the same calculation. And then you add these numbers 5, 7, 15, 3. But again, there's no carryover. That makes it actually easier than in that case. So here we get 4 if we add them up. These like terms, they are now like terms. That's why we arrange them that way, right? So this is 4r. This would be 4 plus 5 minus 8, that's minus 3r squared. This would be minus 2r cubed. And this would be r to the 4th. Okay, and then the pluses here. Now that's the characteristic equation. Now how does it, what we need to do, remember, go back and see how did we find the characteristic equation, we would write the other terms, the lower degree terms on the other side, so we have to switch the signs. And then this would become an, this would become 1 less, 2 times an minus 1. The coefficient, of course, is the constant coefficient is 2. The constant coefficient here is 3, so that's an minus 2. This is minus 4 an minus 3, and this minus 4 is minus 4 an minus 4. Degree 4, because our characteristic equation is degree 4, and that we could also have figured out here because we have one root with multiplicity 2 and another root with multiplicity 2, so in total we had a characteristic equation of degree 4, and that's why we have a recurrence equation of degree 4. And so that's what I wanted to, that's what the problem now is. So given this guy here, it's a solution to, this recurrence relation. Okay, nice, right? So you have this general, this kind of particular thing that looks a bit like a geometric series, but it's more complicated than that. But you can find a recurrence relation for it. That might be very interesting also when you have a particular series, that sequence, you say, okay, where does it come from? And it comes from a recurrence relation there. Now you say, what about the initial conditions? Well, we have it already. We don't need to know I could calculate the initial conditions if I want to, but there's no need to, right? I have what I need. If I want to calculate the initial condition, what should I do? Well, I would have to plug in n is 0 in here, n is 1 in there, n is 2 in there, and n is 3. Because how many additional conditions I need? As many as a degree, so 4. But let me not do that, that's just plugging in, that's kind of silly, right? Okay, so let me do one more example, and I want you to try it yourself now also. So what we have here is an is equal to 2 plus n squared 2 to the power n plus oh no, sorry, 2, sorry, no, I copied this one. 2 plus n plus 3 minus n squared plus 4 plus 4n. That's it. Same question. Think a little bit about it, okay? Try it yourself, but I'm going to go on. Well, first of all, it looks like there's something missing here because we normally have these exponentials, right? There is no exponential here. What is really happening, I hope you see this, right? What is really there, I'm doing it in green, is 1 to the power n. Okay, the basis of these exponentials were the roots. So we have a root here, the root, this gives root 2. And what is the multiplicity of this root? It's the degree of this polynomial that's in front of it plus 1. So the multiplicity is 2 again. What is the root here? The root is the base of this exponent, so the root is 1. What is the multiplicity? Don't say 2 because there are 2 terms. No, 3 because it's a degree 2 polynomial and you have to add 1 to the degree. So the multiplicity here is 3. And what is this then? The root is, that is clear, right? 4. What's the multiplicity then? Well, it's just a constant. Well, that doesn't even look like there's a constant. What is the constant there? 1. So, in any case, it's degree 0. The polynomial in front of it is a constant, it's degree 0, so the multiplicity is 1. Okay, so from that analysis, I know now what the characteristic equation is. These are the roots and these are it. And with a given multiplicity, so x minus 2 squared, that is this. Then this is x minus 1, the root, to the power 3, the multiplicity. And then this is x minus 4 to the power 1, which we don't write. Now you say, oh, professor, come on, now I have to work this out. Okay, so what I will allow you to do is once in a while use Wolfram alpha or something like that. So you can use, especially for when it comes to getting doing homeworks and trying out yourself, you can use this software that helps you do kind of silly calculations. Or even if you do the calculation by hand, you can use this to check your calculation. Now, Very, very important. It's not something you can use on a quiz. Okay? Now, this particular thing, I will not ask you to do something complicated like that, but I just want to give you an example. So what you do then? Well, you plug in here. Wolfram Alpha, if you have not used it yet, is quite smart. It understands quite a lot. So you can ask them questions about, for instance, if you do calculus, you could ask what's the derivative of this and such function. Now here we're trying to just get an expansion here, and even without telling what we really want, I'm just gonna put in the equation. So x minus 3 to the power 2 x minus 1. Oh, I don't know whether this was a capital X, and this might be something that he doesn't like. Yeah, that's my iPad just does this. Okay, x minus 1 to the power 3 we said, right? To the power 3, and then x minus 4. I hope I have it right here. I copied it from my sheet. Okay, let's see what it does. Equals to, we could have said expand or do something. Let's see, is he giving me anything? Yes, for instance, he gives me a lot of stuff, all things that I don't want to know, but the thing that I wanted to know is the one here, the expanded form. Okay, you see this here that I kind of try to highlight a little bit. So now, I don't know, let me see, can I copy this? Copy, let's copy this, and let's see if I can paste it into my thing here. Sorry, I've never actually tried this, so perhaps this might not really work. Okay, no, it seems to, oh, perhaps I need to copy this way. No, I don't think I can copy that way. Now here. Oh, it copied it as a link and not as the thing that I wanted. Okay, let me see, one more try. Technology, right? Plain text. Okay, plain text. Okay, here is the plain text. So let's see whether I can copy it now. Copy it. Oh, it said copy it. Okay. Let's see that is true. So do this again here. Copy. There we go. It's not exactly it. You see it, right? We can read it. It used. I know why it looks a little bit funny. I used this particular font here. So let's put it in regular font. Okay, changed again. No, not favorite. Just put it in American typewriter. Okay, so here now we can read it a little bit better. So this would be now. So what we do then with that, remember, this is a characteristic equation. We have to single out the highest degree and put everything else on the other side. X to the 5th minus 66x to the 4th plus 166x cubed minus 217x squared plus 141x minus 36. I hope I didn't make any copy errors. And then the only thing we need to do is replace this by recurrence relation, right? The coefficients are the coefficients of the recurrence relation, and what we get, well, the highest degree corresponds to the AN, and then the lower degrees corresponds to the previous ones. That, remember, recurrence is relying or calculating your value from the previous values, and we go down by steps of 1. So the 13 would be the coefficient of AN minus 1, the 66 would be the coefficient of AN minus 2, and I keep going down. And how many times do I go down? Well, as many times as the degree, right? Which would be here 6 minus 36, AN minus 6. So degree 6. That was a degree 6 recursive relation of this given sequence. Okay, that's what I just wanted to do. I give you a couple of homeworks there, and as I said, you can use Wolfram Alpha to actually work it out, although I don't make this high degree, so I think you can do it also by hand. And I hope that makes you better understand the relation between the characteristic equation and the solution set. That's what I'm trying to say, is this knowing one is knowing the other. Okay? All right.